Hello, everybody. Today we will speak about compact operators. So we continue at chapter 8, and so the last part of chapter 8, some information about compact operators. So first, let us recall some things from I guess it was chapter 2. So definition 2.8, so if we have a metric space and A is a set in this metric space, this set is called totally bounded. If for every positive epsilon, there exists a finite epsilon net for A. That is, for every epsilon, A can be covered by finitely many open balls with radius epsilon. And we have seen that if a set is totally bounded, then this set is bounded. The opposite is not correct in general. Moreover, we have theorem 212. So if we have a metric space, K is a subset in this metric space, then the following statements are equivalent. So this set K is a compact set if and only if K is totally bounded and complete. In particular, if the space X is itself complete, then it is enough set of completeness to consider closedness. That is, in a complete metric space, K is a compact set if and only if K is totally bounded and closed. So in the sequel, we consider a complete metric space, namely a Banach space. And we will discuss compact operators only on Banach spaces. Of course, one can extend this notion for norm spaces, probably even further, but we don't need it. We don't need to go into this depth, so we stay in the setting of Banach spaces. So definition, we have X and Y Banach spaces, and we have a linear mapping from X to Y. This mapping is called compact or compact operator if the closure of the image of the unit ball with respect to A is a compact set. This means that A maps a bounded, A maps a bounded set, unit ball, into a totally bounded set. Because if the set is compact, it is totally bounded. So since A is a linear operator, it is enough to check only for one set, a unit ball. But from this one obtains the statement for all sets. Is that clear with this?
Yes.
Okay. So about notations, the set of all compact operators will be denoted by K from X to Y, and K of X means that we consider compact operators from X to X. Okay, so this is the definition. Now some comments. So first comment that compact operators are bounded operators. Yeah, it follows actually immediately from this, because so what is the norm of operator? It is a supremum over, okay, so I recall, so the norm of A is supremum over this open ball. So let me write down. Absolute value of A of X. But since this guy is compact, it is also a bounded set, and hence, if this set is bounded, there is a constant which is, so that is, supremum is attained, and it is a constant which is bound, which is a finite constant. Okay?
Okay.
Good. So we go further, some examples. So the zero operator, which acts as follows: take any vector and map it with 0, and you obtain 0. Not map, multiply it with 0. So map any x into 0. This what makes the zero operator. Then this operator is a compact operator because the image of the whole X is just this set. And this is a one-point set, and this is a compact set. Okay, agree?
Yes.
Okay, next example. So if X is infinite dimensional vector space, then identity operator is not a compact operator. Why? Because, so by this corollary, but what is it about? We know that in an infinite dimensional normed space, all balls are not compacts, are not relatively compact. That is, even the closure, uh, or even a closed ball cannot be a compact in infinite dimensional vector space. That's why this set for identity operator, it cannot be compact. Okay. Next example, if A is a bounded linear operator such that the image of the whole space under A and its closure, its vector space, if its dimension is finite, then A is compact. Because if this vector space is finite dimensional, then this set in this set space is closed, yeah, because we have closure, and bounded. Yeah, we have just shown it. But in finite dimensional space, all closed and bounded sets are compacts. Okay, so is it clear with this?
Yes.
Perfect. So some special case. In particular, if we have a Hilbert space X, and X0 is a subspace of X, and X0 has a finite dimension, then the orthogonal projection on this finite dimensional subspace is a compact operator, exactly by this statement. So we have at least one non-trivial example of compact operator. So orthogonal projection on a finite dimensional subspace. Okay, now we discuss some basic properties of compact operators. They are formulated in theorem 816. So let X, Y, Z be Banach spaces. So first statement is that the set of all compact operators from X to Y is a closed subspace of all bounded linear operators from X to Y. And hence, this set is itself a Banach space. So it is a closed linear subspace of a Banach space. And hence, it is Banach space itself. Of course, we mean the operator norm on this set. Second statement, if A is a compact operator from X to Y and B is a bounded linear operators from Y to Z. So the standard picture, I like draw pictures. So X, Y, Z. So here we have A, here we have B. So if one of these two operators is compact and another is a bounded linear operator, so here or here, then their composition is a compact operator. In particular, if all these spaces are the same space X, then the set of all compact operators on X forms a two-sided ideal in the algebra Lx. And the third statement is that the operator L, a given operator L is compact if and only if its adjoint is compact. Okay, so our aim is to prove this theorem. So for proving part 1, we need the following lemma. So lemma 17, so let X, Y be normed spaces. Let A be a bounded linear operator and a set M be totally bounded. Then the image of a totally bounded set is again totally bounded under such mapping. Further, if we have two totally bounded sets in two different norm spaces, then Cartesian product of this set is totally bounded in the Cartesian product of the spaces. And further, if we have two totally bounded sets in a space, then their linear combination, that is, what is it? I guess you know, this is the set of all points alpha x plus beta y such that x belongs to M, y belongs to N. So this set is also totally bounded. So linear combination of totally bounded sets is a totally bounded set. So this is an exercise. There is nothing so difficult. Okay, so now we are going to prove the theorem, and we start with part one. So we show that so compact operators form a closed subspace in the set of all bounded linear operators. So first thing, let we have two operators A and B, which are compact operators. We want to show that the any linear combination of such operators again belongs to this set. That is, we first want to show that this is a linear subspace of this space. So let us consider this unit ball in X. Then, by properties of images, so if we consider the sum of operators, so this is a new operator, and this operator, so the image of the unit ball under this operator is a subset of this set. No, I don't like it like this. Let us make it here. Plus B of unit ball. And moreover, this operator, so image of the unit ball under this operator lambda A is just lambda lambda times this A of unit ball. What does it mean? This means, hence, by lemma 817. So we know that A and B are compact operators, hence these sets. So since A and B are compact, then the closures of these sets are compact sets. Hence, without closure, we have just relatively compact sets. So the sets whose closure is compact, and such sets should be totally bounded. So we know that this set is totally bounded, and this set is totally bounded, and hence, and this set as well. And hence, by this statement, we know that this set and this set, as subsets of such sets, they are also totally bounded. Hence, by lemma 817, A plus B of this ball and lambda times A of the ball are totally bounded. And hence, this A plus B belongs to the set of compact operators. And lambda A belongs to this set of compact operators. That is, this set of compact operators is a linear subspace of the set of all bounded operators. Okay, actually the word subspace already means that it is a vector subspace. So I just use this linear to emphasize it once again, to stress it. Okay, now we want to show that this is a closed subspace, not just a subspace, but a closed one. Okay, I will try to start here. I don't remember how many slides I have. Well, like actually sufficiently many, but okay, let us try here. So now let Kn be a sequence of compact operators and K be a bounded linear operator. And we assume that Kn, the sequence Kn converges to K when n tends to infinity. Converges to K in the operator norm, that is in this space. So we have a sequence of elements here. This is a subspace of this space. We assume that this sequence converges in this space to an element K. Then, for any positive epsilon, there exists natural number big N, such that the norm of Kn minus K is smaller or equal to epsilon for any n bigger or equal to n. What does it mean? So again, I recall that the norm, operator norm, as I have written somewhere, where, here, so norm, it is, roughly speaking, the radius of a ball, the smallest radius of a ball, which contains the image of the unit ball under A. Sorry for long. Sorry. So since we have this means that Kn of a unit ball is an epsilon net for the set K of unit ball. That is, we may approximate any point of this set using points of this set, and the quality of approximation will be not worse than epsilon. Okay. Since Kn is a compact operator, the set Kn B1, 0 is totally bounded, and hence there exists a finite epsilon net for this set. Agree? Agree or not?
Can I ask why there exists a finite epsilon set?
Because
Epsilon height.
once again, Kn is a compact operator. That is Kn bar of B1. So the closure of this set, by definition of a compact operator, the closure of this set is a compact set. Hence, without the closure, this set should be totally bounded. So once again, coming back to the very beginning of this lecture, K is compact if and only if K is totally bounded and closed. Yeah. So if you forget about the closure, yeah, so relatively compact set, it should be totally bounded. Once again, relatively compact set is a set whose closure is a compact set.
Okay, thank you.
There is also the terminology pre-compact, pre-compact, or relatively compact. So it's a set whose closure is a compact set. So if we have a totally bounded set, its closure is compact. So if we have a set whose closure is compact, this set is totally bounded. So coming back to the proof. So we have a sequence of compact operators which converges to some bounded linear operator K. So we approximate K by Kn in the sense of the operator norm, and hence we approximate this set via this set. But this set is totally bounded, hence there is a finite epsilon net for this set. And hence the same epsilon net for this set is automatically 2 epsilon net for this set. And hence this set is also totally bounded, because for any positive epsilon, we are able to construct a finite epsilon net for this set. Okay, so I have said it. Now let me write it down. For that, I need to go to the next slide. So Kn is compact, hence this set is totally bounded. Hence there exists this a finite epsilon net for this set. This net is simultaneously a 2 epsilon net for the set K of B1, 0. And hence this set K B1, 0 is totally bounded, and hence K operator K itself is compact. That is below the set K. The operator K also belongs to this set. So every Cauchy sequence in this set converges to a limit again in this set. Hence, this set is compact. I also may recall the following. It was a lemma in lecture 3. We have discussed this lemma. So if we have a metric space, so a set is totally bounded if and only if every sequence of elements from A possesses a subsequence that is a Cauchy sequence. And a set is compact if it is totally bounded and closed in a complete metric space. In this sense, this means that every sequence of elements from A possesses a subsequence which converges to an element of A again. So this is what we have used here. So sequential compactness and compactness are equivalent in metric spaces. Okay. And the same for closure. Sorry, now I have said something not quite nice. So we have shown that the set is closed in this sequential sense. So using the sequences. So this is a lemma about total boundness, but this is something wrong. Sorry. So once again, what we have done, we have taken any sequence from this set, a Cauchy sequence, which converges here. And we have shown that its limit point lives in this set again. Hence, this set is closed. For metric spaces, because this is a metric space, norm space with the operator norm, it is enough to deal with sequences only to show the closeness. Okay?
Okay.
Perfect. Now we go further and we show part 2. Part 2. So if A belongs, if A is a compact operator, B a bounded linear operator, or vice versa, then the composition is a compact operator. So we consider only one case. So let A be a compact operator, B be a bounded linear operator or continuous linear operator. It is equivalent. Then, A is a compact operator, hence the image of a unit ball is totally bounded in Y. Yeah, because the closure of this set must be compact by the definition of a compact operator. And now we take a totally bounded set and apply a bounded linear mapping. That is B of this totally bounded set, A of B1, 0, is again totally bounded in Z by lemma 817 part 1. So I open this lemma once again. So if A is a bounded linear mapping, then it maps totally bounded sets into totally bounded sets. So this is what we have used. Okay, so is it clear what has happened? Sorry, where we are? We are here. So A is a compact operator, so it makes from bounded set a totally bounded set, and then the second mapping is a just bounded linear mapping. It maps totally bounded into totally bounded. Also in opposite direction, we first okay, so I will write down just similarly for A bounded. What's going on? And B compact. Yeah, so if the mapping is bounded, so it maps bounded set into bounded set, so this is a bounded set, and then compact operator maps bounded sets into totally bounded sets. So finally, this composition will be a totally bounded set. Okay, is it clear?
I think it's clear.
Perfect. Okay, so now we need to show part 3. So A is compact if and only if A star is compact. So let us first show one direction. So let K be a compact operator. let V be a unit ball in the set Y star. So what we want to show? We want to show that this operator is a compact operator. That is, we want to show that the image of the unit ball from this set is totally bounded. So we show that okay, so I have used A, not K. We show that wow, A star of V is totally bounded in X star. So let me draw a picture once again. Probably it will be here. So X, Y, X star, Y star. This is A, this is X, this is Y. Here we have A star, Y star, X star. So here I have V, and here I have A star of V. Okay. So we want to show that A star is compact, so we check the definition. That is, we have to show that this set is totally bounded. So we show this, that the set is totally bounded by lemma 211 of lecture 3. This is what I have already showed you. I will show you it once again. So this is this lemma. So a set is totally bounded if and only if every sequence of elements from this set possesses a subsequence that is a Cauchy sequence. So it does not need to converge to an element of A because A does not need to be closed. Yes, but you see, every sequence possesses a Cauchy subsequence. Okay, is it clear what we are going to do?
Yes.
Okay, so let us realize it. So we realize it. So first step, let U be the unit ball in X. That is, it will be here, U. Since we know that my operator A is compact, then the closure of, so A of U, the closure of this set is a set in Y. So A of U. So the closure is a compact set. By definition of a compact operator. So let us remember it. Now we want to show that this set is totally bounded. So we take any sequence from this set and find a Cauchy subsequence. But this set, it is the image of the set V. So every sequence here is the image of sequence here. So we start from V. So let Fn be a sequence in this set V. What does it mean? This means that the norm of all these Fn's is small or equal to 1. Yeah, they are elements of a unit ball. But what does it mean? This means that the sequence Fn This is a set. It is a bounded set in the space of all continuous functions defined on a compact set A of U bar. Yeah, so recall once again that V lives here. What is Y star? Y star is the set of all continuous linear mappings on Y. Continuous linear mappings. It is a subset of the space of all linear mappings. So they are defined on the whole Y. In particular, they are defined on this compact subset of Y. Okay?
Okay.
Perfect. But this is a nice set. It's a continuous functions defined on a compact. So we know some criteria. What does mean a totally bounded set in this space? This is the Arcelor-Ascali theorem. And by Arcelor-Ascali theorem, for a set to be totally bounded here in this space, the set should be bounded and equicontinuous. So this set, so let me continue my writing. So we consider such a sequence. We know that this set is bounded, is a bounded set here. Moreover, since all functions Fn are continuous and linear, yeah, because yeah, they live here in this set, in this space of continuous linear functions. We have that absolute value Fn of y1 minus Fn of y2 is smaller or equal than the norm of Fn times y1 minus y2. And this guy, we know it is small or equal to 1. That is all functions Fn are Lipschitz continuous with Lipschitz constant smaller or equal to 1. That is the set of the family of all Fn's is equicontinuous. So we have a set. It is a bounded set in this space and it is equicontinuous. So hence we may apply Arcelor-Ascali theorem and claim that this set is totally bounded in this space. And so in order to write it down, I have to open the next slide. So I'm waiting a second. So may I go further?
Yes, please.
Perfect. So we say that hence by Arcelor-Ascali, it was a theorem 217, lecture 4, and I will open it now. Yeah, so we have a space of continuous functions on a compact set. The statement is that a set is compact if it is closed and totally bounded. And totally bounded means bounded and equicontinuous. Okay, so this is exactly what we are going to use. So by this theorem, hence by this theorem, this set of Fn's is totally bounded in the space C of A of U bar. Therefore, by lemma, this is my by lemma 211, sorry, which I have shown you already. So this was this lemma. If a set is totally bounded, if and only if every sequence possesses a Cauchy subsequence. So we apply it to this totally bounded set. So therefore, by lemma 211, there exists a subsequence f and k subsequence of the sequence fn, such that the norm of nk minus f and m, norm in this space, this is a supremum norm, yeah, tends to 0 when k and m tends to infinity. So Cauchy subsequence. Okay, Cauchy subsequence, perfect. And now this is like a preparation. So we have prepared everything. Now coming back to what we want to show. So we want to show that this operator is compact. So we want to show that this set is totally bounded. So we take any sequence from this set, then it is the image of a sequence here. So next step, so consider A star of Fn. So any sequence in this set, any sequence in this set has this form where Fn is a sequence in V. So this sequence possesses the subsequence, probably a subsequence. A star F and K, such that norm A star F and K minus A star F and M operator, not the operator norm, so the distance in this space, yeah. So this set lives in this space. So we consider the distance of elements in this space, but what is it? This is the space of all continuous linear functionals on X. So this is supremum over all X's in U. Recall that U is my unit ball in X. Absolute value of A star F and K of X minus A star F and M of X. Now recall the definition of a joint operator. This is supremum over all X's in U. And now I use definition. It was definition 8.1 of definition of a joint operator. which we discussed last time. This is fnk of ax minus fnm of ax. But this is nothing else but supremum. Now this is my y. Hence we have supremum over all y's in the image of U. Absolute value of f and k of y minus f and m of y. But this is just the norm of f and k minus f and m c a of u bar. And we know that for any sequence fn, we may construct a subsequence which satisfies this. So starting from here, we come back to the corresponding sequence fn, and hence to the corresponding Cauchy subsequence, and hence lift it to this level. Okay, this means that for any sequence of elements in this set, we are able to construct a Cauchy subsequence. Hence, by lemma 211 again, this set is totally bounded. To 11. Okay.
Okay.
Good. So we have shown one direction. It was one direction. So if sorry. So if A is compact, we have shown that A star is compact. Now we go to the opposite direction. So let A star, which is an operator from Y star to X star, be a compact operator. By the first part, so by this direction, which we have already shown, we have that the operator A2 stars, which is the mapping from X2 stars to Y2 stars, is compact. Yeah, because this guy is just adjoint to this guy. Not adjoint, sorry. Yes, adjoint. Joint to this guy. So, but how this guy is related to this guy? So A2 stars compose this canonical mapping GX. So this is a canonical, I don't remember how I denoted it before, probably like this. And X is an element of X, is the same as we first take X, apply A, and then lift it to the level of 2 stars, so to the level of bidual. This happens for any X in X. Again, a picture. So here we have A, which acts from X to Y. Here we have A star, 2 stars, which acts from X2 stars to Y2 stars. And we have gx, and here we have gy. So let me kill these brackets because too many symbols. Okay, so is it clear what has happened here? This is element of this set. This is element of this set.
Okay.
Where so gx maps x into x by dual, gy maps y to its by dual are canonical mappings, they are isometries. This we have discussed, I guess. So this is the statement. So let us clarify it in a more detailed way. Indeed, for any element of y star, we have so A2 stars applied to gxx. So A2 star applied to something, it is element of this guy. That is, it's a, so what does mean this guy? It's a set of continuous linear functionals on this set. That is, this guy is a continuous linear functional here. That is for any element of this set. We apply this continuous linear functional to this element. And what does it mean? Now we use definition of adjoint, definition 8.1 of a joint operator. This is gx x evaluated at the point A star of f. So here we have this guy is element of x2 stars, then A2 stars applied to this. This is an element of y2 stars, and this is the element of y star. Now, after applying the definition of adjoint, we have here element of x2 stars, and this is the element of x star. Okay, so it's a linear functional, oops. It's a linear functional on x star. But what is written here? So what kind of linear functional it is? It is a point evaluation. It is a point evaluation at the point x. So by definition of the canonical mapping, so this linear functional acts on this element as follows. We just evaluate this element, which is a continuous linear functional on x at point x. And hence, on this level, we use again definition of adjoint operator. This is just f of a x. But what does it mean? This means that here we apply to f a linear functional which is a point evaluation of this f at the point ax. That is what is written here. By definition of this guy, it is nothing else but gy. So point evaluation at the point ax. So before I wrote it here as a sub-index, but sorry for changing the notations. Here, I guess it is more natural to write it down as it is written here. So we use this functional, we apply this functional to this element f. Okay, so what we have, so for any f, so the action of this functional on f is the same as the action of this functional on f. So this is exactly what is written here. So we have just checked, we have checked that this holds. Okay, and now what do we have? We assume that this guy is compact operator. So so let us finish the conclusion. So we have this formula. So this is the relation of so we have started with A star is compact. Then by this part we have obtained that A2 stars is compact. Now we want to make a conclusion about A. So this is the relation about A2 stars and A. But if you analyze this relation, you see that so A2 stars is a compact operator, and this is an isometry. This is also an isometry, which so isometries preserve the distances. So what is the conclusion? Hence, so A2 stars of the set, which is the image of a unit ball in X under the canonical mapping. It is the same as the image under the canonical mapping GY of A of the unit ball in X. This is a subset of the set of a unit ball in the space X2 stars. But we know, so yes, since this guy is an isometry, so it preserves distances. Hence, the image of a unit ball under an isometry is a subset of a unit ball here. But A2 stars is a compact operator, so A2 stars of a unit ball is a totally bounded set. So this guy is totally bounded because we know that this guy is compact operator. Okay, and hence this guy is also totally bounded. Agree?
Yes.
Yes. Okay, so this guy is oops. Hence this guy is totally bounded, but this is an isometry, hence this guy is totally bounded. So hence, okay, not only this guy, but also this guy is totally bounded. Conclusion, oops, hence A is compact. Okay. So one needs more time to trace or to track all the small things here, but nevertheless. So this set is totally bounded, hence this set is totally bounded, but this exactly means that A is a compact operator. And yeah, so how to check that isometry preserves totally boundedness? Once again, you may use this lemma. Yeah, so if a set is totally bounded, every sequence possesses a Cauchy subsequence. But after isometry, distances are preserved. That is, if we had a Cauchy subsequence, so after applying the isometry, it remains to be a Cauchy subsequence. So using this criteria or this description of a totally bounded set, one can check that isometries preserve. But actually it follows from lemma 817 because isometries, they are bounded and linear operators, and hence bounded and linear operators map totally bounded sets into totally bounded sets. So that's it. We are finished with this theorem. Okay, so these are the basic properties of compact operators. Okay, let us go further. Remark. So if we have a compact operator, then the image of the whole space under K, since K is a linear operator, this is a vector subspace. So it's a vector space, but moreover, this is a separable vector space. Why it is separable, even if X not a separable space? Because the image of X under K can be represented like this, yeah, because X is a union of such balls. Hence, by the properties of images, K of X can be represented by like this. But since K is a compact operator, then image of a unit ball is totally bounded, and hence image of any other ball, since K is a linear mapping, it is also totally bounded. So this set is totally bounded. Hence, there exists a finite epsilon net for any epsilon. And hence, if we take a union of all such nets for each fixed n, then we obtain at most a countable set. And this will be a countable and dense set here in K of X. For any n due to linearity of K. So K is compact, hence for n equal to 1, this is a totally bounded set, and there is the epsilon net. For all others n, using the linearity of K, one constructs the corresponding epsilon net. Okay. So is it clear here?
Yeah, it's clear.
Perfect. We go further. Examples. So one of important examples of compact operators is integral operator. So let K be a nice function of two variables, which is continuous with respect to both variables. Oops. We use this function as a kernel of integral operator. So we consider the space of continuous functions defined on 0, 1, interval 0, 1 with supremum norm. And we consider the integral operator as an operator acting in this space. And it is the integral operator with kernel K. So any element will be assigned to a function of T. It is a continuous function of T, again, due to properties of the kernel. And you integrate X with this kernel with respect to S. So such operators are called Fridholm integral operators, and K is called the kernel of integral operator. So the statement is that this operator K is a compact operator. So let us show it. So consider So consider M, which is the set of all elements Kx, such that X belongs to this space, C01, and the norm of X, supreme norm is small or equal to 1. So this is just the image of a unit ball, closed unit ball under the mapping K. So first statement is that M is bounded. How to show it? Supremum over all T from 0 to 1. Absolute value of K of X, Kx of T. This is supremum over all T. Absolute value of integral K Ts X of S ds. And now we can estimate it. This is the supremum norm of X times supremum over T integral from 0 to 1 absolute value of K Ts ds. Agree? Standard estimation of operators. And now this is smaller or equal to 1 for because we consider M. So we use this. And this is some constant, which is finite because K is a continuous function on this square, so continuous with respect to both variables. So integral over a segment, finite bounded segment, Riemann integral of a continuous function is finite. We have a continuous function again, and supremum of a continuous function of a compact set is attained and is finite. So we have something, so we have a constant here. That is, all elements of M live in a ball with radius given by this constant. Okay? So M is bounded, it's clear?
Okay, it's clear.
Perfect. Exercise to show that this is exactly the norm of K. Okay. But this is an exercise. Now we show that this set M is equicontinuous. And we use again Narcelas-Kali's theorem. M is equicontinuous. So since K is a continuous function on this square, then for any positive epsilon, there exists delta positive, such that, since K is continuous on this square, this is again a compact set in R2, and hence this function is uniformly continuous on this square. So I'm writing down this, but in a special way, which I need. So for any epsilon there exists delta such that for any 2 points t and t prime from interval from 0 to 1 with the distance t minus t prime smaller than or equal to delta, we have that absolute value k of ts minus k of, this is my k, so k of ts minus k of t prime s is smaller or equal to epsilon for any s in this interval. So this is just a consequence of uniform continuity of a continuous function on a segment. Then we consider absolute value of my operator k at xt minus k xt prime. This is smaller or equal than integral from 0 to 1 absolute value k of ts minus k of t prime s, absolute value is closed, times absolute value of xs ds. So we again are interested in m. So everything what happens is in m. So my x's are from m. So not x's, kx's. So these are functions from my m, from this set. Hence, this is small equal to 1 due to this condition. And this is by our assumption. So for any epsilon, we take delta such that for any 2 t's with this condition, this stuff is smaller or equal than, so we have epsilon here, then everything is smaller or equal than epsilon. So this happens. So this estimate, yes, so this estimate happens, yeah, for a, for any x such that kx in M. So for any element here. This means that this set is equicontinuous. So this set is bounded and equicontinuous. Hence, this set is totally bounded by Arcelà-Ascali theorem. But I need to open a new slide to show it. To write it down. So may I go to the next slide?
Okay, please.
Yes. So what is the conclusion? The conclusion is that the closure of M is compact by Arcelà-Ascali theorem. Again, it was theorem 217. But this means exactly that K is a compact operator. Because what was M? It was the image of a unit ball under K. Okay? So we have shown everything. So it's nice to work in this nice space because here we have Arcelà-Ascali theorem. So we may check compactness of some sets, and hence we may check if a given operator is an integral operator or no. Recall that M, it was just the image of a unit ball. And this bar is this bar. And it was even so. But if this set is compact, then the set which is given in the definition is also compact because it is a closed subset of a compact set. Okay, so we go further. We may consider this operator also, this same operator, but in L2. So now my kernel should be a little bit slightly different. I mean, this is okay, but we may consider a more general case, namely the kernel is given by a function which is L2 function on the square, and this is the Lebesgue measure in R2. And we consider the same operator as the operator acting from L2 into L2. So the statement is again that this operator, even as a mapping here, it is again a compact operator. Well, I do not prove it. It stays as an exercise. For this, you need to do similar things, but you have to use Fubini theorem, Kashibonikovsky-Schwarz inequality, etc., etc. But I hope the idea is clear. So such operators with nice kernels, they are compact. Okay. Note that if the kernel is symmetric, so this is a complex conjugation, then this operator K is not only compact but also self-adjoint operator. So we are not going to show it, but just recall that Kxy, L2 is a nice Hilbert space. So we consider a joint in the category of Hilbert spaces. This is just integral from 0 to 1 scalar product. And now I insert my operator. It is integral from 0 to 1, kts, xs, ds. So this is my k. Times y of t bar dt. Now with Fubini, you may interchange the integrals and see that if this happens, then this is the same as x ky L2. Okay, so it's a kind of combination. So we have compact operators. We also recall some that we studied self-adjoint operators, not so just last time. Okay, we go further. Remark. So if X is a Hilbert space with infinite dimension and K is a compact operator, then there is no inverse operator to K in this set of bounded linear operators. So no one bounded linear operator can be inverse to K. So why? So this is the proof. So assume that there is the inverse, that is the operator T such that Tk is the same as Kt. So this composition and this composition are the same, and they're equal to the identity operator. But we have proved theorem 816 that if we compose bounded linear operator with a compact operator, we obtain a compact operator. So no matter in which order we compose. First compact and then bounded, or vice versa. First bounded and then compact. Such composition by theorem 816 gives us a compact operator, but it should be identity if we speak about the inverse. And identity is not a compact operator, which we have already mentioned today in an example in this situation. Okay, is it clear?
Yes, it's clear.
Perfect. But we may slightly generalize the notion of inverse. And what's going on further, I present the operator, which is, in a sense, the inverse to K. And this operator is not a bounded operator, but still it's a very nice operator, namely, so typical example, we consider this space. And this is the operator. So I'm going to show you that this guy is, in a sense, the inverse to K, to some K. And we will see which K is meant. And now this is the space, Hilbert space. This is the second derivative operator with some boundary conditions and defined not everywhere, but only with the suitable domain. So we take C2 functions, twice continuously differentiable functions. Of course, this is a subset of this set. So this operator, so we would like to solve this equation for y elements of the same space. So we consider A as an unbounded operators from x to x with this domain of definition. We take y from x and try to find x such that this equation holds. So let us solve it. So ax is equal to y is equivalent to this differential equation. This is ODE. So let us solve it. So we integrate in the following way. We integrate from t to 1. So when we integrate both sides from t to 1, the left-hand side gives us the first derivative at 1 minus the first derivative at t. And this minus will give the signs here. So we have these identities. Now I use my conditions, boundary conditions. So this boundary condition kills this item, and I have again ODE. So the right-hand side is just a function of t. The left-hand side is the first derivative of my unknown function. Hence, I may integrate once again. Now I integrate from 0 to t. So this is the integral of the left-hand side. This is the integral of the right-hand side. So after integration, the left-hand side looks as follows. And I again use my boundary condition. So this disappears. So we have only x of t. And here we have this integral. This is a double integral. Now let me, so we calculate this integral. And it turns out that we obtain this. So let me demonstrate how it happens. So we have this double integral. What does it mean? So we integrate with respect to s and with respect to tau. So I consider this integral. So this is a diagonal. Diagonal is s is equal to tau. So here we have 0, here we have 1, and here 1. And here we have t between 0 and 1. So we actually integrate over this domain. Let me say that this is a domain D, and this is the integral over the domain D. Integral over D, ys, ds, d tau. So I would like to interchange the order of integration. So here you see ds from tau to 1, and d tau is from 0 to t. This is one order. And now we change the order. We integrate with respect, we integrate over this domain. That is d tau, or what else? So s will vary from 0 to 1. So we consider from here to here. and tau varies from this curve to this curve. But this curve is just again exactly this minimum between t and s. Okay, so when we interchange the order of integrals, we obtain this. But this integral can be calculated, and this is exactly what is written here. Okay?
Okay.
So we have solved this equation. So if A is given by this operator, then this equation gives the following solution, which we may understand as the action of integral operator on y. And K is exactly the compact integral operator, Fridholm operator, as we have seen just before in the example. And this is the kernel of the Fridholm operator. And this is a nice function, which is, of course, an L2 function on this square. Okay, so roughly speaking, you see, so A is a kind of inverse to K, or K is a kind of inverse to A. And moreover, you see that this function is, of course, symmetric with respect to T and S. So this operator K is even a self-adjoint operator. But actually, this A is also a self-adjoint operator when we weaken the definition so that we consider not only bounded but also unbounded operators. Okay, so this is a summary what we have done. So with a suitable extension of domain of definition of this operator, one may consider A as a kind of inverse operator to K, unbounded inverse. In which sense inverse? So this is a definition. So if we have a Hilbert space, let the operator T be an unbounded operator defined from, so we consider it as an operator from X to X, but with domain of definition and its image. So there is a domain where T is defined and there is the image. So if we assume that this operator T is injective, then we may consider the inverse mapping as a mapping from here to here. And then what do we have? We have that this composition is equal to, so t to the power minus 1 tx is equal to x for such x's, not for all x's, but for such x's. And the opposite direction, t composed with t to the power minus 1x is equal to x for all x's here. Okay, so then this guy is the unbounded inverse in the sense that this holds, but not on the whole x, but yeah, so this is just a mapping with this domain and this image. Okay?
Excuse me.
Yes?
The Hilbert space is not necessary, right?
Yes. But now, yes, Hilbert space is not necessary in the definition, of course. We are just here in the Hilbert space. That's why it has survived here because we are here in the Hilbert space. But of course, we need just a norm space. Or actually, we need two sets. So X is a set, T is a mapping. Yeah. Of course. There is nothing special in Hilbert space here. Well, so as I said, with a suitable extension of domain of A, one may consider A as the unbounded inverse. That is, yes. So unbounded inverse should be defined here. That is on the whole image. So this is not the whole image of K. We don't need such smoothness. So actually the extension would be W to 2. To get exactly this. This is my T, and this is my A with the proper extension of domain of definition. Okay, and this extension is actually a self-adjoint operators. And this is the definition how to define a self-adjoint operator in the case of unbounded operator. So this formula, as before, should hold, but not for all x's and y's in the whole space X, but just in the domain of definition of A, but it is not all. Also, this condition should be satisfied. And this condition means that we should be careful with boundary conditions. So they are used exactly to reach this identity. Okay, but we don't go deeper into this. Just please pay attention that so this is the message. Solution operators for boundary value problems for partial differential equations. For example, for elliptic, yeah, we don't need to stay in a one-dimensional case. So we may consider Laplacian operator in a bounded domain with proper boundary conditions, or more general elliptic operators in the bounded domain. So, and then then this would be an elliptic partial differential equation. So solution operators for boundary value problems for such type of partial differential equations are often given by Fredholm integral operators, like here. So this method is well known in the theory of PDEs, and this is known as the method of green function. So this is the green function for this simple task here. So the kernel of resolving operator, yeah, so if we have a differential equation, it's natural that the solution is given by integral operator. It's natural to expect. And in many cases, it is really so. So the method of green function, it is the method which allows to solve PDEs by finding proper green functions, that is kernels, suitable kernels of integral operators. Okay, so actually it is not the whole story about compact operators. And I will continue, but if you have to leave, please leave. If you have time, just stay with me. Anyway, we record this meeting till the very end. And I hope this message was sufficiently clear to understand why we discuss compact operators at all. They are important operators in the theory of PDEs. So let us investigate this family, so this set of operators in more details. So let X be a Hilbert space. Then the set of all compact operators is actually the closure of the set of all bounded linear operators with finite dimensional images. Moreover, if my Hilbert space is separable, then so any Hilbert space has an orthonormal basis, but if the space is separable, an orthonormal basis is at most countable. So there are at most countably many vectors in it. So if we take a separable Hilbert space, take any O and B in it, then each compact operator on X can be approximated by orthogonal projectors. By orthogonal projectors on finite dimensional subspaces spent on the vectors of O and B. So this holds. So if we prove this, then at least for separable Hilbert spaces, we obtain this statement. Yeah, because we know that such spaces are finite dimensional. We have already discussed that orthogonal projection on a finite dimensional subspace is a compact operator. with finer dimensional image. And the statement is that any compact operator can be approximated by such compact orthogonal projectors. Okay, so I'm going to prove this theorem. It is an important theorem. And it also says how far from such operators or how far from such operators we can go and remaining to be good. So remaining to be a compact operator. So actually not too far away. So let us prove first this statement. So we prove first item 2. For this, we need the following lemma. Lemma 22, compactness criterion in a separable Hilbert space. So let X be a separable Hilbert space with an orthonormal basis En. A set M in this space is compact if and only if it is closed, it is bounded, and this following criteria holds. So that is the behavior of tails of elements of this set is good controllable, so to say. And actually, this criterion we have already seen, but it was formulated for a particular Hilbert space, L2. But actually, each separable Hilbert space is isometrically isomorphic to L2. So the proof is just to make this isomorphism to L2 and prove there. So, and the proof there, it was an exercise for you someone many chapters ago. So we assume that it is already known. And now let us prove the theorem. So this is what we are going to prove. So let X be separable, K be a compact operator in X. This means that this set K of a unit ball and then the closure, it should be a compact set. But hence, by this criterion, which we have seen here, we know that this should be fulfilled. Hence, I write down this condition about the tails. The tails should behave themselves very good. It was lemma 822. So if this is a compact set, then its description is satisfied. That is, the tails are good. The tails of all elements from this set. Moreover, if we consider the norm of operator k minus pnk, so Pn is the projector on the first n, on the subspace which is spanned on the first n vectors of the orthonormal basis. So let me consider this squared. So this is then, so what is the norm? This is supremum over all x's in a unit ball. And here we have norm of kx minus Pn kx norm in x, and everything is squared. Now I call this guy y. Then this is, of course, this object is something non-negative. So if we first take supremum and then square Or if we first square and then take supremum, nothing changes. So this is equal to supremum. Now I take, if my x is here, then my y is here. Image of a unit ball under K and the closure. And here we have y minus p and y norm squared. This is the norm in y. Oh, okay, sorry, in x again, because y is equal to x, yeah? Everything happens in the same space. Sorry. Yes. Now I recall that, so if I have a vector in a Hilbert space, then in the orthonormal basis, in this given orthonormal basis, this y has the following form. This is I from 1 till infinity. Here scalar product y and ei times ei. Hence, if we consider Pny, what is it? This is the sum of first n summands. Yeah, orthogonal projection on the first n coordinates. Okay, agree?
Yes, agree.
Yes. So then if you subtract from y this guy, you obtain exactly the tail. So what you obtain is as follows. It is supremum over all y's in this KB10 bar. And here we have sum I from n till infinity, n plus 1, sorry. And here yen, ei, and then squared. So I have used squared, so the norm. But this tends to 0 when n tends to infinity by this. Okay. So we have shown what we wanted. We have shown that this guy tends to 0 when n tends to infinity. We have shown part 2. Is it clear?
Yeah, it's clear.
Perfect. Now let us show part 1. Part 1. Since the operator K is compact, okay, not since, let K be a compact operator. Then K of the whole space X and then the closure is separable by remark 818. We have discussed it already, that this is a separable set and this is a vector space and the closed vector space, and it is a separable closed vector subspace of X. Hence, it is a Hilbert space itself. Hence, there exists an orthonormal basis, En, in this Hilbert space. I will write it down even. In the Hilbert space K of X bar. Consider then Pn, which is the projection on the span of the first vectors E1 up to En. Hence, by this item 2, K minus P and K tends to 0 when n tends to infinity. Yes, we are here. But that's it. So we have x, we have taken any compact operator. Then we work here. We take an orthonormal basis. And as soon as we work here, this is separable. And we are coming back to the item number 2, which is already proved. And this means that we may approximate K by such operators, but these operators are with this condition, because Pn is a projection on a finite dimensional subspace. So we have approximated K by operators from this set. That's it. Okay, we are almost finished. Just a few comments. So remark, so the statement of this theorem also holds in Banach spaces, but not in all Banach spaces, but in Banach spaces that have a Schauder basis, but not in all Banach spaces. So you see, compact operators can be approximated by such nice operators, not only in Hilbert spaces, but also in Banach spaces with Schauder basis. So for a long time, it was not clear if this true for all Banach spaces. But then there was a counterexample constructed by Enflo in this year. And you may see some details and references in the book of Conway, which I have already advertised. And also there is another counterexample, a later counterexample in this year. So it just shows that this space, it's a Banach space of all bounded linear operators on a Hilbert space H. So this is a Banach space where this is not true. And this is the way to show that this space does not have a Schauder basis. There is no Schauder basis in this very important for applications space. Okay, so you see compact operators, they are important for applications due to their relation to differential operators. So one solves many partial differential operators by means of compact operators, roughly speaking. Of course, with some, there are some things extra beyond. But nevertheless, this is the main application of compact operators. And you see that in good spaces, we may understand what means a compact operator in the sense that they are able to approximate them by some nice operators. In particular, this approximation can be constructed by applying this particular sequence of orthogonal projectors. Okay, that's it for today. Thanks for your patience. Do you have any questions or comments?
I have two questions.
Yes,
The first one, could you please go to page 39?
yes,
Okay, um, for this proof,
yes.
I think maybe we need to add the proof that all the finite rank operator is a compact operator.
Yes, yes, yes. But I guess it was an example somewhere in the very, very beginning. So we have discussed some examples of let me see. Yes, yes, this is exactly what you said.
Aha, yes, yes.
Yes,
Okay, then it's okay.
perfect.
Uh, then next question is, could you please go to page 26?
26. 26. Sorry, probably I could do it somehow more fast, but I don't know how to do it. Yes?
Yes. Okay. And I want to ask that here you said In term 2, similarly, let now K belong to L2, and
Yes.
the measure you choose the product measure of one dimension, the big measure,
Yes.
right?
Yes.
Uh-huh. So basically, this is not the big measure on the plane.
Why? It is because we extend in both cases from a ring of not a semi-ring of such boxes. Yeah, with half open sides, I guess.
Mm,
So this is
as
the
I read,
Lebesgue, so this is
Mhm.
the notation for Lebesgue measure in R2, and it is so it is a product of one-dimensional Lebesgue measures. Because so if you start already from R2, you extend, so you get to the big measure by starting from a ring, a semi-ring of nice sets, but they are Cartesian products.
Mhm. But what you said is the construction of the big measure exactly on R2. It's not the product, the definition of the product.
No, no. So this is okay. This is a standard notation of a Lebesgue measure in R2, but this is a
Uh-huh.
standard notation because the Lebesgue measure in R2 is nothing else but the but the product of one-dimensional Lebesgue measures in R1.
Ah, okay. Maybe I have some misunderstanding of this notation. Can I
Yes,
ask
maybe.
that sometimes I say some people use, for example, a Hilbert space H and with the same notation, H product 2.
Yeah,
So,
Cartesian product of Hilbert spaces. Okay. Okay, well, you see, there are not so many symbols, and there are much more ideas in mathematics than symbols. And so people have to somehow use the similar symbols for many different notions. So it is not about tensor product of Hilbert spaces or whatever, but it's a product of measures, this is a measure which is obtained by continuation of a product. Okay, so you start with such a semi-ring of such boxes. So you have sides of these boxes, and then this, let me call it mu. So mu of such a box, b times a or a times b, is just um, lambda 1 of b times lambda 1 of a. Yeah, so it is a kind of lambda times lambda defined on a semi-ring. And then you extend this Caratador, you do this Caratador extension from semi-ring to the smaller sigma algebra, which contains the semi-ring. You obtain a Borel sigma algebra. And the corresponding Lebesgue, so this extension is denoted not by this guy, but already with this guy.
I see, I see. Thank you. Thank you very
Yeah,
much.
welcome. But I delete this because
Ah, okay,
it
of
is not
course.
related to the topic, so to say.
Yes.
Okay, so further questions or remarks? Okay, then I stop the recording.